at Institute of Physics. She is currently working with Professor Pankaj Agarwal, and she obtained her PhD from IISER Kolkata. And today, her research interests broadly are in quantum information, graph states, hypergraph states, and today she is going to talk on multipartite entanglement, the properties, the various kinds of multipartite that is being used in different quantum information processing tasks, and also different measures to detect multipartite entanglement. So we welcome you, and now the stage is yours. Thank you.
Thank you for this nice introduction, and good afternoon to you all. And thanks, sir, Professor Prashanta Panigrahi, for organizing such a beautiful and big event. And also thanks to my juniors and lab mates to successfully carry on this event. Now, today I am going to discuss something about the multipartite state. This is nothing but the just generalized, not my work specifically. This is just an brief idea. Let's start. This is the outline of my talk. First, I will give an introduction. After that, I will discuss about 2-qubit system and entropy of entanglement, concurrence, 3-qubit multipartite states, and absolutely maximally entangled EMA states. First, we in this long session, we many times we people, our professors, juniors, seniors, all have discussed about many things about entanglement. Till it is an introduction. I am going to give a brief introduction. Entanglement. First, when we come to entanglement, once if we discuss about one composite system, it is said to be entangled if the constituent system cannot be described independently, though they are separated by long distance. Suppose we consider two particle system, like two subsystems like A and B, and if it is a pure state like psi AB, then if it can be written in the form of a product state like this, psi AB equals to psi 1A tensor product psi 2B, then the state is separable. If the state psi AB cannot be written in the form, the state is told to be entangled. Similarly, the same thing will happen for the mixed state also. In mixed state, we describe the state using density matrix. The mixed state is entangled if it cannot be written in the following form: rho equals to sum over of I, pi, rho I A, tensor product rho I B. This is the rho I A and rho I B are the density matrices of the system A and B. If this cannot be can be written in this form, and this is a condition like rho I is always greater than equal to 0, and sum over of pi is equals to 1. If it cannot be written in this form, then the state is told to be entangled. Otherwise, it is separable. Now, we will come to the example, like for a 2-qubit system, psi AB, this is a product state like 0A and 0B. It is separable. If we add two superposition of product state, like here we add, this is a superposition of two product state, like this is one product state and this is another product state. This cannot be written in these, after that these individual state cannot be written as a product state. Thus, it is an entangled state. Now we will come to the 2-qubit system. A generalized 2-qubit system can be written in this form: psi equals to alpha 00 beta 0, 1, gamma 1, 0, and delta 1, 1. But using local unitary transformation, we can reduce it to the two terms, like just simply alpha 0. Maybe this alpha can be replaced by anything else. Suppose A1 0 0 plus B1 1 1, whatever. Just we can represent this general two qubit state just by two terms, and simply one parameter by normalization condition, like one parameter, another is root over of that very parameter, 1 minus that very parameter, because of the normalization condition. So two qubit maximally entangled states are Bell state. This is very well known. Like we found four set of Bell states, like 5 plus minus. This is one. Another is psi plus minus. And we will come about the how to measure the entanglement. We can compute entanglement in various measures. Like I will discuss two of them. That is one, entropy of entanglement and concurrence. There are many more. Negativity. You can consider tangle. You can consider also geometry measure of entanglement, also coherence measure of entanglement. Coherence measure can be two kind of. One is matrix for any of the subsystem. If it is non-zero, that is the subsystem is in a mixed state. It indicates that two subsystems are entangled. Suppose we take one state having two subsystem A and B, psi AB, that is phi A and tensor phi B. It is a separable state, as we see. Then the reduced density matrix, rho A, phi B, phi A, outer product of phi A, is a pure state. Thus, entropy of the state is 0. Similarly, if you take the similar density matrix of the reduced density matrix of the system B, it will also be a pure state and will also have the 0 entropy. Thus, reduced density matrix having a non-zero entropy is therefore a signal of the existence of entanglement in the system. And also we just mentioned the von Neumann entropy as this. Also, it can be written as the eigenvalues of the system, like just replace some trace of lambda and log lambda. This is the lambda I is the lambda at the lambdas are the eigenvalues of the density matrix, and entanglement entropy for Bell state is 1. Now we come to the concurrence. Concurrence provides an important measure of entanglement. It was first coined by Hill and Wouters in their 1997 PRL paper. It is very well known and rigorously used. It is very well used measure of entanglement. It is positive for entangled state and vanishing for separable state. First, concurrence was developed for only the 2 qubit system. If we describe a 2 qubit system with density matrix rho, then the concurrence of the system C rho will be maximum of the 0 and lambda 1 minus lambda 2 minus lambda 3 and lambda 4. Here lambdas are the eigenvalues of the system R. What is R? R is given by this, where rho tilde is a spin flipped state of rho. Now, later concurrence is generalized for that for in qubit system. Generalized concurrence, I concurrence. There are very kind of measure of concurrence, and Bhaskara and Panigrahi have developed one measure of generalized concurrence based on the wedge product. We will later discuss about that. Suppose we consider an in-particle system 1 to n, and it is a pure state, and we can write their density matrix as the outer product of bra and kate of the state psi. And next, if we want to discuss the in-particular particles whose bipartite separability from this composite system is our interest, and obviously the cardinality of m should be less than n, that is the total number of particles. Then the generalized concurrence em for the bipartition m prime, where m prime is the complementary set of n, that is n minus m. Then it can be measured by this form, em squared is equals to as this from, this from, and this from. This is also this pattern form is also used in various places. Now we will come to the 2-qubit concurrence based on wedge product. 2-qubit concurrence can be, suppose we consider one 2-qubit state. 2 qubits, this is a general 2-qubit state. If I can write these 2-qubit states as this, just taking common b, just 0b common from the this part and this part, and 1b common from b and d. And if we define, just define this as this chi0a and another is chi1a as two vectors. If we take this wedge products is nothing but the generalization of the cross product. If they are parallel, like this two vectors are parallel, we know that two parallel vectors, the cross product of two parallel vectors are 0. Similarly, the cross product of the two parallel, wedge product of these two parallel vectors are always 0. If the cross product or wedge product of these two vectors are 0, then they are separable. So we understand from this aspect that for separability, the vectors from this composite state should be parallel. Otherwise, if they are not parallel, they will form an area. And then the concurrence will be given by 2 of mod of this area, chi0 wedge chi1. This is the wedge mod of this wedge product, and this is done by Bhaskar and Panigrahi in their 2017 paper. Also, concurrence for bipartition also can be expressed by the area of a parallelogram spanned by the post measurement vectors. These vectors can also be told as a post measurement vector. Now, this is developed by Banerjee and Panigrahi in their 2020 paper. Using this parallelogram, the area of the parallelogram is proportional to the concurrence. Now we will come to the concurrence for multipartite state. Concurrence for the for an n-qubit system, the total entanglement is the sum of all concurrences for all bipartition. Like for 3-qubit state system, the total entanglement is E, that is equals to ABC plus BAC and CAT. For 4-qubit system, the bipartition will be more, and we will have these 4 bipartition from single cut and another 3 bipartition ABCD, ACBD and ADBC from 2-cut or bipartite 2-qubit bipartition. And for the simplification, like single cut bipartition like ABC, BCA, like this one. The concurrence for the corresponding bipartition is simply 2 of determinant of rho A, where rho A is the reduced density matrix of the system. Here we have taken one example. Entanglement of 3-qubit GHZ state is E equals to this. GHZ state is 0, 0, 0 and 1, 1, 1. And adding these 3 bipartition, we will get the total entanglement or total concurrence. Now we will come to the 3-qubit multipartite states. There are very well-known 3-qubit multipartite states like GHZ state, W state, and GHZ class of state, W class of state, cluster state, and many more. Just we first see GHZ state as this W state, and W there are many phase parameter can also be there. Cluster state also is there, but cluster state can be transformed. The 3-qubit cluster, specifically 3-qubit cluster states can be transformed into GHZ state using local unitary transformation. And also we have another 2 kind of states like graph state and hypergraph states. this is one graph state. Graph state is a set of sets, that is a family of sets containing one vertices set, another is edge set. Like here we see there are three vertices, one and edges are three, like 1, 2, 2, 3, and 3, 1. And both of these combination vertices and edge completely describe one graph. And after using just some application of some gates, we can convert this graph to a graph state. And this is another state. This is hypergraph state. Hypergraph state is a generalization of graph state. In this case, what we see, one edge can connect just two number of vertices, like 1, 2. It is connected 1 and 2. Here we see 1, 2, 3 is connected by a single edge. This is the difference between graph and a hypergraph. Just a hypergraph can any number of vertices. Whatever the number is, hypergraph can one hyperedge can contain the full set of vertices. And here is a simplification of these states. This is G1 and this is hypergraph G2, H. And also we can say that hypergraph contains the graph, like graph is the subset of hypergraph. Now we will come to the entanglement of entropy for the 3-qubit states. So let us denote the entropy of entanglement for each bipartition ABC as EA, EB, and AC. And EA is nothing but the von Neumann entropy of the reduced density matrix rho A. For understanding, we may some pure state. One of its reduced density matrix is pure state. Like this is not mixed. So the von Neumann entropy is 0. So we can conclude that the state is biseparable. That like this is, we can find like some state like that is ABC, psi ABC equals to phi AB, tensor product phi C, anything. If that cannot be can be written in the format of pure state or any other format, pure state format, its entropy will be 0. And for that reason, these states cannot be told as a genuinely maximally entangled state. GME or maximally entangled state. And what we see that the entropy of entanglement for GHG state is 1. For W state, this is this, and clustered state is 1. All are 1. And for 3-qubit system, this is the maximum. That like for 3-qubit, this is absolutely maximum. No states will be found to be more entangled that like each bipartition cannot be more than 1. And graph state G1 in this example, this one, it is also having the same values 1. But hypergraph states in the above example, this is 0.8. For 3-qubit states, GHG state is told to be maximally entangled. Now we'll come to another example of that very biseparable states. Here is also I described one graph state. This contains only one edge connecting 1 and 2, and there is 3 edges, but connection is only 1. 3 vertices, sorry, and connect only 1 edges. And if the state can be written in this form, and it also can be simplified in this form, like this is a product kind graph. This is a 2 entangled state product, one pure state. And immediately what we see that entropy of this state G2 is like this is EA and EB is 1, as because this is a product state. As because this cannot be written as a product state, this is one entangled state, and each bipartition of A and B cannot be written in the pure state format, but EC is 0, as and it is biseparable. And graph state in 2B represents the cluster state. This is a cluster state. Also, this also imply the cluster state means this is the GHG state. Under local unitary transformation, this state can be represented as a cluster state. GHG state. Next, this is the generalization cluster state as a graph state. Here we see that various example of 2D cluster shapes. The vertices are the qubits, and our edges in it is indicate the connectivity like 1 2 2 3 3 4 4 5, and based on this connection you can easily convert this cluster to a graph state. Cluster states are easily understood to be a graph state. Now what we see, this is a 4 qubit state, 4 qubit GHZ state. This is also a graph state. This is also after some simplification, this state can be written as a graph state, as GHZ state. Now we'll come to the absolutely maximally entangled AMA state. Absolutely maximally entangled states are those multipartite states, multipartite quantum states that carry absolute maximum entanglement in all possible bipartition. Precisely, the reduced density matrix of each bipartition is maximally mixed. Maximally mixed means the identity by dy, that is a dimension. AMA states are known to play a relevant role in multipartite teleportation, quantum secret sharing. They are very much important in various aspects. And AMA states are explored very rigorously, and no AMA states are found for 4 qubit and 7 qubit system. And we already knew that GHZ state for 3 qubit, 2 qubit base states are maximally entangled. These two states have the property that their one-party reduced density matrix are maximally mixed. But in qubit, GHZ state is not always the maximally entangled state. There are several 4 qubit states which are found to be more entangled than GHZ state. Example, HZ state, a few cluster states. HZ state is developed by Higuchi and Sudbury, and this state is expressed as this, and while omega is exponential of 2 by I by 3. Entanglement entropy for the 2-cut bipartition, like this is a 4 qubit, so we will have 1 cut bipartition and 1 cut, and here we did not show 1 cut bipartition because 1 cut bipartition cannot be more than 1, and already GHZ state has 1 cut bipartition 1, that is a maximum. We just here show the 2 cut bipartition. Entanglement entropy of the 2 cut bipartition of HZ state is this, and GHZ 4 is 1. Just they all have 1. This is another pattern of omega. This is one of the cluster states, and it has ABAC as 2 and another is 1. But 4 qubit cluster state, for 4 qubit cases, the cluster state is not GHZ state, and also it cannot be converted to GHZ state using local unitary operation. Till now, the 2 qubit entropies of the reduced density matrix of each state is told to be global maxima in 4 qubit cases. And it is not possible to find a 4 qubit state with all AB, AC, AD values are 2. Or AB, rho AB and rho AC and rho AD are maximally mixed. And this is the summary what I am going to say. This is a just brief introduction about entanglement and entanglement study and multipartite states, and how multipartite state, very different kind of multipartite states, maximally entanglement, entropy of entanglement. That's it. And thank you all for listening. Thank you.
So thanks, Ramita Di, for the beautiful presentation.
Thank you.
So audience can ask question if you have, or you can write the question on chat box.
I have questions. Thank you for your talk.
Thank you.
Why? So clarification. Why do you call cluster graph edge states? Are there any patterns to classify them?
Actually, yes, cluster state as graph state. You are asking about cluster state as graph state, right?
Yes. Are there any patterns you
Yes, there
use
is.
to identify them?
This is a pattern, like cluster can be written in this form, or they can be expressed as a, I mean, cluster shapes are there. There can be, and each state is already this is not kind of Hughes and Sudbury. They developed the state for the maximal entanglement kind of thing. Sorry, what is the state? Yes, and this cannot be, this H state cannot be replaced in by graph or anything like so, but JG state can be expressed using graph. And this, there is like pattern, you can see the pattern like for 2-qubit state. Okay, where is this? For 2-qubit, like 2 edges will be there, 1, 2, 2, 3, and this will be reduced to a JG state. And for 4-qubit, this is the edge will be 3, 1, 2, 1, 3, 1, 4. Maybe for 5-qubit, there will the edge will be 1 more, like 1, 2, 1, 3, 1, 4, 1, 5. This kind of combinations will be there.
So next, there is any other question? If it is not, then we'll move to our next talk. And thanks again, Ramita Di.
Thank you
And
to you all.
lot of things got to learn from your talk. So it was very beautiful.
Thank you.
Okay, bye.
Bye.